Okay, thank you very much for the nice introduction. So, and thank you for coming back to the tutorial. So in this part, I'm going to present one of my recent work on combining learning and queuing. This work is actually based on joint work with Weikang, Xiaojing, and Mark from Purdue ECE department. So this work is at the intersection of queuing and learning. So by queuing, I'm broadly referring to the area about performance modeling, network utility maximization, as we've seen in the previous parts of the tutorial, and also Lyapunov-based stochastic control. So this body of research has an in-depth understanding about how to deal with uncertain agent dynamics. For example, the arrival process of a client to the system. But in many applications that we're going to see later, we also face uncertain agent features. So here, agent, I mean, could be the clients or the servers. So for example, in the online advertisement problem that Shrikant mentioned in his part of the tutorial, so there's a click-through rate. So when you place an advertisement to a client, whether this client will going to click the advertisement is actually unknown to the system. So the click-through rate, since it is unknown, but this is actually very crucial for making optimal decisions. So often in the queuing literature, they assume this piece of uncertain agent feature is actually unknown. Okay. So on the other side, there's also a huge body of research on learning uncertain features. It includes like offline learning from the historical data, for example, the collaborative filtering, and also the online learning from online feedbacks, such as multi and bandits. And this body of research is actually develops very sophisticated and algorithms and theory to resolve uncertainty in agent features. But the weakness is that they often assume a fixed instance without agent dynamics. So for example, in the classical multi and bandit problem, there will be a fixed agent pulling different arms. There's no agent arriving or departing to the system. So now what if we have both uncertain agent dynamics and also uncertain payoffs? Okay, so it seems like we need to somehow combine queuing and learning. So that is we are interested in this work. And our interests actually are motivated also by operation of online service platforms. So recent years have seen a surge of online service platforms ranging from the applications in advertisement to hotel rentals. And these online service platforms actually bring the customers and providers together. A very key problem faced by this online service platform is that how to assign clients in the system to servers to maximize the total system payoff and subject to some server capacity constraints. Okay, and then in these applications or in these online service platforms, we typically face uncertainty in both agent dynamics and the agent features. So here are just 3 examples with these both types of uncertainty. So for example, in the online shopping platforms such as Stitch Fix, so the clients can be customers who are interested in buying clothes, and servers corresponds to stylists who recommend clothes to the customers. And then the customers arrive and depart in these online service platforms. And then the payoff to the system is actually the customer satisfaction. And now it is crucial that like when a stylist recommends a clothes to a customer, this customer satisfaction is actually unknown to the system operator. Okay, so that's why this customer satisfaction actually has a significant uncertainty in this case. Similar story can also happen in the online advertisement. There, the clients are advertisers, and servers correspond to slots on web pages for displaying ads. And we face uncertain dynamics because advertisers go and depart in the systems. And we also face uncertain features because the click-through rate, as I mentioned earlier, is actually unknown to the system operator. And this also happens in the crowdsourcing scenario where the clients can be the poster jobs and servers are workers. And then their jobs arrive and depart to the system. And then if you're given a job, like the quality of the answer, the quality of the work is actually also unknown to the system beforehand. Okay, so in all of these examples, we need to somehow to, on one hand, we need to do the queuing control in response to these uncertain agent dynamics. also we want to learn the uncertain features. As we're going to see in the talk, just picking a good algorithm from each field actually will not work very well. So our key contribution in this work is to develop a utility-guided online learning and task assignment policy, and then we prove this policy actually has a very low regret. So here's the outline of the rest of the talk. By the way, if you have any questions, feel free to stop me. So I'm going to first present our system model. So our model is actually inspired by the earlier work by Johari and Campbell and then Kanoria. So on the left-hand side, we have clients arrive to the system according to a Bernoulli process with rate lumped over n. So the time is slotted at each time with probability lumped over n. There will be a new client arriving to the system. And then for each new client, it will bring a random number of tasks. And we assume the number of tasks actually is geometrically distributed with mean n. So the total arrival rate for the task actually equals lambda. So in the context of online advertisement, you can think about clients are the advertisers, and tasks actually corresponds to different ad campaigns of the same advertiser. In the online shopping, you can think about clients are customers. Then this task corresponds to the clothes that need to buy for this particular customer. Okay. On the right-hand side, then we have in total J servers. Okay. And then server J actually serves exactly mu J task per time slot. We actually, toward the end, I'm going to tell you a little bit more about when the service time actually also could be random. But here we assume the service time is deterministic. It's equal to mu J. Okay, so now the system needs to assign tasks to servers. Now the crucial thing is that if a task from client L is completed by server J, then the system observes a payoff feedback. And this payoff feedback is random and is Bernoulli distributed with some unknown mean. Okay? And the goal of the system is try to assign the task to servers to maximize the total system payoff. I also want to mention that if all the tasks of a particular client have all been served, then the client will depart the system immediately. Okay. So this is essentially our system model. If the payoff parameters, like the payoffs of client L assigned to server J were null, this is actually a typical queue control problem. And then actually the focus would have been to deal with uncertain dynamics in that setting. And in particular, we can use the backpressure maximum weight kind of policy to deal with the uncertain dynamics. And we can show that you can achieve the optimal like Oracle payoff to some extent. But now the main difficulty in this model is that these payoff vectors are unknown to the system. Yes? Okay, yeah, that's a good question. So I need to explain a little bit about my notation. So star here just means the true payoff. It's the underlying truth that systems do not know. Without star just means estimate. So once you have a star, just think about its underlying truth you do not know. And then L denotes the client L, and J denotes the server J. Okay, so we call this payoff vector as a vector of when you're varying the server J. Okay, so in this case, since we do not know the payoff vectors, then we somehow need to combine queuing with learning of the payoff these vectors from the Bernoulli feedback that we talked about earlier. Okay, remember, system will observe Bernoulli payoff feedback if the task has been finished the service. Okay, so we actually, for the analysis, we're going to add a very mild assumption, distribution assumption on these underlying unknown payoff vectors. In particular, we're going to assume that for each client L, her unknown payoff vector is actually randomly generated according to a discrete finite distribution. So capital I actually denotes the number of possible different payoff vectors. And then her unknown payoff vector equals one of the possibility, like the ith possibility equal to rho I. Okay? And then in this case, we just say the client is of class I. Okay? But note that the system actually do not observe the payoff vector. Actually, the system also do not know the underlying distribution. Okay, so this is just for the define the system model. And then according to this, then the arrival rate of class I just equal to lambda times rho I. So that's the arrival rate of a particular class. And this is also unknown to the system. Okay. So now in order to define a performance metric, let us first try to understand what's the best possible performance that you can get. So here we're going to consider an oracle scenario where this oracle has access to the perfect information about all the uncertainties. Then in this case, you can get an upper bound R star as an optimal value of a following optimization problem. So Pij is the average fraction of task from class I assigned to server J. And then the objective here is nothing but the average payoff per unit time, subject to two constraints. The first constraint is just saying the server capacity constraint is not violated. And the second constraint just means this indeed is a valid probability vector. So sum of assignment probabilities equal to 1. Okay? So it is not hard to show that this R star actually provide an upper bound to any policy in the long run. Okay? But now certainly the issue is that we do not have this perfect information for the system. Yes?
What are the lambda I?
Okay, yes. So lambda I is the arrival rate of class I. Okay, so let me backtrack a little bit. So lambda is the total arrival rate of task. And then lambda times rho I is actually the total arrival rate of a particular class I. Okay? Okay, yes. And then again, C star actually denotes the true underlying payoff. Okay. So let us work on a particular example of this upper bound to get some feelings. And also this will give us some useful insight. So this is a very simple scenario. We have two classes and two servers. And for each class, the arrival rate is equal to 0.6. Okay? And then the server, you have two servers. The server capacity is all one. And then the payoff vectors are given here. Okay? So now we can try to work out the oracle upper bound. It's actually not hard to, the optimal solution turns out to be that for class 1, you're going to split the traffic between server 1 and server 2. And for class 2, you assign all the traffic from class 2 to server 1. Okay, so let's see why this is the case. The first thing is that you realize both classes prefer server 1 because you get a higher payoff 0.9 here, right? But now the crucial thing is that server 1, the total service capacity is only 1. It's actually less than the total arrival rate, that is 1.2. So server 1's capacity is insufficient to support both classes. So you have to kind of kick someone out in server 1. Okay, so which class you need to kick out? It turns out that we need to compare the second preference. So for class 1, the second preference, like payoff is 0.3, is higher than the second class. So if you really want to kick out one class, it's better to kick out class 1. Okay? Since its second preference is actually better. And now, in particular, we're going to split the traffic from class 1, like a route 1/3 of the traffic to server 2. The reason is because under this case, then the total arrival rate to server 1 will be exactly equal to 1, the service capacity. Okay? So that's the optimal solution. From this, at least we get two useful lessons. The first one is that this optimal decision actually depends not only on each client's own payoffs, it actually depends on all the client's payoffs. For example, in this case, if class 1 was unknown, then the class 1 will never pick server 2. Okay, class 1 picks server 2 is because of the congestion at server 1. The second lesson that we can get is that so some low payoff servers often need to be avoided, even if they're available. Okay, for example, in this example, server 2, under the optimal solution, the total arrival rate is actually 1/3. So there's a substantial amount of time the server 2 will be available. But actually, according to the optimal solution, you should not assign tasks from class 2 to server 2. Okay, so you need to avoid some low payoff servers, even if they are available. Okay, so that's the oracle upper bound. Now, remember, in this Oracle upper bound, we assume the payoff parameters actually are exactly known. But to the system, we do not know these payoff vectors. So things can get even worse. So to define a performance metric, let's look at an online policy pi and define this expected payoff of this policy pi at a given time horizon capital T. So suppose there's an NT clients in system at time T. So PLJT here is again is an awkward notation, but that corresponds to the mean number of tasks that going to assign from client L to server J at time T. And then you times the true payoff C star. Okay, so that is the payoff that you can get according to the this online policy. Note that here the payoff is actually the true payoff because we're looking at the expected value of the payoff. And also note that here it is okay to use the true payoff, define the performance metric, even though the system actually does not know these true payoffs. Okay, so now with this expected payoff, then we look at the regret as a difference between to the Oracle upper bound. And we want to design an online policy which has a small regret. Okay, so that's essentially our system model. At a very high level, you can actually view this problem as a dynamic multi-bandit problem, where in the sense that there's a rival stream of clients, and each client corresponds to a multi-bandit problem, and each server corresponds to an arm. And then for the system, like for each client, the system needs to decide like whether to pull an arm, like select a server, and then which arm to pull, okay? And also note that there are only limited number of opportunities to pull an arm at a given time because there's a service capacity constraint. So in some sense, the system needs to combine or balance the queuing and learning process among different clients, okay? To balance since the different clients actually are competing for these opportunities to pull an arm, okay? So that's essentially our system model. And now, next I'm going to present actually two failed attempts before actually presenting our policy. So the first attempt is that motivated by this multi-banded point of view, actually a very natural way to estimate the unknown payoff is using this classical estimator called the upper confidence bound. So here CJLT denotes the upper confidence bound, like estimator of the payoff for client L to server J. This equals here the C bar actually denotes the empirical average of the payoff that has been received so far by client L to server J, okay? And then we add this adjustment term. This adjustment term actually captures the uncertainty in the estimate. So in particular, this HJL actually denotes the number of tasks that have been assigned from client L to server J. And this H actually denotes the total number of tasks that are assigned from client L. So notice that when HJL increases, like when this client L keep pulling server J, then this adjustment term decreases because the uncertainty actually decreases. So you add this adjustment term to make sure that this estimator, UCB estimator, is always above the true payoff. So that is why it's called upper confidence bound. And here, since the true payoff is always below than 1, so we truncate it at 1. Okay? So that is a UCB estimator. It's a natural way to estimate the unknown payoff. But now remember, we have a system of clients and servers. So that actually a natural way to combine this UCB is try to maximize instantaneously total payoff for the system. So in particular, so we are going to find assignment which actually maximize the instantaneous total payoff where we plug in the UCB estimate for the payoff vector. And then subject to the server capacity constraints. Okay? So that's a natural kind of approach. But now the question is that, okay, will this work? The answer is actually unfortunately no. So the reason is that this policy is called Myopic Matching is actually too nearsighted. It focuses too much on maximizing the instantaneous payoff and then ignoring the future payoff. This can be seen by this running example, where here record that optimal solution is given by this, and you can easily work out the Oracle upper bound of the payoff is given by 0.96. But now if you look at the myopic matching, so even though here I assume the UCB estimates are perfect, okay. So for myopic matching, it turns out that whenever in the system you find at least 2 tasks, then if the server 2 is available, then 1 task will be assigned to server 2. Okay, but then if a task is assigned to server 2, the highest payoff they can get is 0.3. Okay, so it turns out that the overall payoff is actually no more than this number. Okay, and by the way, in the system, most of the time you will see there are at least 2 tasks. Okay, so you can see this number is actually strictly lower than the Oracle upper bound, even though I'm now benign saying that UCB estimates are exact. Okay, so the crucial lesson that we learned is that this myopic matching policy focuses too much on the instantaneous payoff. For the optimal policy, we need to consider not only the instantaneous payoff, but also long-term dynamics. And speaking about long-term dynamics, that's from the previous part of the tutorial. Actually, we learned a lot about how to deal with long-term dynamics. And in particular, the queue-based control is actually very good at this. So in particular, we're going to start with the Oracle upper bound. And then as we can view this as, I think it is y less or equal than x. We can introduce like a dual variable, qj here. You can interpret this as a shadow price for the congestion at server j here, right? And now, since you have a shadow price, then the net payoff that you use for the assignment is actually equal to the true payoff, subtract this shadow price for the congestion. And then for each class, the decision is very simple. You just pick the server with the largest adjusted payoff. Okay? And then how to update this shadow price? Again, you can use this very simple dual update that explained in the by Shakeout in the first part of the talk. Okay? In particular, the intuition about the dual update is that, once again, if the total assignment probabilities for server J exceeds the capacity, then there's more congestion at server J. So you need to increase the shadow price for the congestion, and vice the other way around. Okay? But now remember, we do not know the true payoff, right, for the system. So then a natural way is just to replace this true payoff by the UCB estimate. And then you can use this queue-based control plus UCB. Okay? So this seems to be a very natural approach. And then will this work? The answer is unfortunately no also. The main reason is actually because queuing will delay the learning. So I'm going to explain why queuing delays learning. So you need to take a closer look at this dual update. This dual variable actually equal to 1 over v times the server queue length. I think in the Shakeout's part of the talk, 1 over v is like epsilon. But here I'm taking v, so think about v is large. So for this kind of queue length-based policy, to be able to track the long-term dynamics, we need to make v as large. Okay, but now if v increases, then as you can see, the server queue actually increases. And now remember, the system only observes the payoff after the task has been finished the service. So if there's a queue at the server J, for example, then for those tasks at this queue, you are not receiving the payoff feedback. So that's why we say the server queue will delay the feedback for the learning. And that means this UCB estimate has to be based on the past kind of received feedback. So the UCB estimator is kind of become outdated and inaccurate. So in particular, this leads to what we call the vicious cycle between queuing and learning. On one direction, so as we explained, queuing can cause feedback delay and slow down the learning process. On the other way around, because of the feedback delay, the learning will become less accurate. So the inaccurate payoff estimator will lead to inefficient decision, which can possibly also increase the queuing. So somehow this closed loop interaction, if not properly managed, then this will degrade the system performance. Here is just one simple numerical result based on this our running example to show that this performance degradation is actually real. So the upper bound, Oracle upper bound is 0.96 here. The myopic matching is actually way below here. And queue length-based control actually does slightly better. But still, when v is large, there's still a kind of big gap to the Oracle upper bound. Okay. The reason is because the queuing delays the learning process. So now I'm going to talk about our policy. Okay, so just a recap, like two important lessons we learned. So myopic decision do not work means that we somehow need to learn the long-term contention levels. The server queue delays learning means that we actually cannot use server queues to infer the contention levels. So this seems to be kind of a dilemma, right? On the one hand side, we want to use queue backlog to learn the contention levels. On the other hand, we cannot really use server queues because that will cause the delay of the learning. So how to solve this dilemma? So our kind of idea is actually coming back to this utility maximization framework. In particular, we're going to use a utility function to guide us in learning the contention levels. So here's this algorithm. Again, we're going to use UCB for the payoff estimator, as I said before. But now, at each time, our policy is going to decide the task assignment by solving this convex optimization problem. Here, crucially, in the objective function, we introduce this logarithm utility for each client. And this PJL here is actually the average number of tasks assigned from client L to server J. Before going to the details about this algorithm, I want to mention that our algorithm actually indeed do not need to know lambda, the arrival rates, do not need to know the mean number of tasks for each client, that is capital N, and also do not need to know the payoff vectors. And actually, I want to point out that our policy actually do not even need this finite class assumption that we imposed in the beginning of the talk. Okay, but to appreciate why this utility is important, yes. Yes. Okay, so let me try to answer the question. So the first thing is that the true payoff is randomly drawn, and after it is drawn, it is fixed. Okay, that's the first thing. And the second thing is that you need to learn these true payoffs from the feedback. And feedback is actually generated after a task has finished the service. So if there's a queue at the server, and then for the tasks in the queue, since they have not been served yet, so you do not receive the payoff feedback for those tasks at the queue. So that's what we mean by delay, the learning. Is that clear? Yeah, so we already assigned the task to the queue, but to the server, but there's a queue there, so you cannot immediately complete the service. You do not immediately see the payoff feedback. So that's the reason. Yeah. Yes?
Why is it not 1? It's just the total per client L. That is just the total rate you're assigning to all the services, right?
Okay, yes. Okay, that's a good point. So here, actually, this is not really the probability. Okay, so this PJL actually roughly is the average number of tasks assigned from client L to server J. This number could be between 0 and could be even bigger than 1. So we're not constraining, it's only non-negative. Okay. And then the constraint actually makes sure that the total number of tasks assigned to server J does not exceed the capacity. Okay. Okay, and actually I want to say that, okay, if you think about this, when there's a lot of clients in the system, so actually this assignment, because of service capacity constraint, this total probability actually will be small actually. Because you need to, if you have a lot of clients, you want to satisfy this capacity constraint, you cannot make the sum of probability even equal to 1. It can be even strictly less than 1. Okay. But let's take a look at the closer look at this optimization to get some intuition behind the proposed algorithm. So the first thing, as I said, is that we respect the server capacity constraint. So the total number of assigned tasks does not exceed the capacity. So there's no queue at the server. Okay, so hence no feedback delay. Okay, that's the first thing. And the second thing is that we introduce this logarithm function. And this logarithm function is a function of the total assignment probabilities for client L. And this actually promotes the fairness among different clients. Okay. And this fairness actually turns out to play two important roles. The first one is that the fairness has an eye for the future. This view is actually inspired by the flow-level congestion control. There, it is actually shown that if the congestion control policy is fair, then it actually can achieve the largest possible stability region. If the congestion control is myopic, for example, maximizing the instantaneously total throughput, it turns out that the congestion control, actually, the stability region is actually strictly smaller. So in this sense, we say the fairness has an eye for the future, and that's actually the crucial thing that we avoid the pitfalls for myopic matching. And the second important role of fairness is actually ensures every client has an opportunity to pull an arm. So every client can learn and explore. So no client is left behind. This will turn out to be crucial in the performance analysis later. Okay? So that's the log utility function part. And the last one that we do is that, remember this UCB estimate is truncated by 1. But here we further subtract by a parameter gamma here. The reason is that we want to prevent the system assigning clients to low payoff servers too aggressively. For example, if you set gamma equal to 0, then once there's a server available, you are going to assign some tasks to this available server. Recall that in the running example, this is actually not optimal according to optimal decision. So remember there, we want to avoid some low payoff servers. So that's why we subtracted by gamma to make sure that we're not selecting too aggressively the low payoff servers. In particular, this can be also seen by looking at the derivative of the objective function, and making gamma to be bigger than 1, this term will become negative. So the system will become more reluctant to assign clients to low payoff servers. Finally, I want to briefly talk about the role of V here. So there's a parameter V here. The crucial thing is that as V increases, the derivative actually decreases. Okay, so what does that mean? That means the system becomes more conservative in assigning clients to low payoff servers. But on the other hand, as V increases, since you're assigning more reluctant to assign to low payoff servers, that will lead to more congestion in the system. And this will also affect our payoff regret in the end. Okay, so that's about the algorithm. Yes?
So in addition to some the benefits that you mentioned, it seems like your algorithm also naturally ensures that no client gets assigned like all their jobs in one time. I mean, it's not like I can come in and all my jobs, my end jobs will get assigned in the first slot itself. That's a nice property because if that happens, then I lose out on learning entirely.
Okay, yes, that's true. Yeah, so I think this is automatically implied by the algorithm that you're not assigning all the tasks at once. This is probably incorporated by the server capacity constraint and also the fairness among different clients. Yeah, it's a good comment. So now let me present our main result. Our first result is actually an upper bound on the mean number of backlog clients. So NT is the total number of clients in the system at time t, and lambda is the total task arrival rate, and mu is the total service rate, and we assume lambda is strictly less than mu. And in this case, we can upper bound the mean number of backlog clients in the system under our policy. This immediately implies the system is indeed stable under our policy. And note that this upper bound actually increased linearly in V. And this is actually kind of same as our previous observation about the role of V. So as V increases, you will have more congestion. So the proof idea turns out to be relatively simple. Yes? So what's the question again? Sorry. Yes. Yes. Oh, I see. Okay. I'm not sure, actually. Yeah, I mean, that's a good comment. So I think the comment is about here, we assume that the total payoff is some linear function. So when you maximize this, that corresponds to some myopic decision, which is something that we want to avoid. But if the payoff function is already some concave, okay, I think my guess is that you probably still need some logarithmic utility function. That's my guess for now, because I think you still need to maintain some fairness. Yeah, so I don't know. Yeah, but I think that's a good comment. Okay, so I want to briefly mention the proof idea is very simple. So like even though our policy is not work conserving in the sense that we're not always using the server capacity, but when the system is very congested, we can show that all the servers will be fully utilized. In this case, the total service rate mu is bigger than lambda. So that's why we can get an upper bound. And in particular, we apply the stochastic coupling to a simple queue with total arrival rate mu in this case to finish the proof. So our second main result is actually more important. It's about the payoff regret. So we look at any like finite time duration t, and then we look at the gap between the expected payoff of our policy and the Oracle upper bound. It turns out that the payoff regret is upper bounded by the sum of 3 terms. Here, the coefficients beta 1, beta 2, and beta 3 are just depend on the system parameters. You can view this as a constant if you do not scale the systems. So the first term actually captures this uncertain dynamics. It actually decreases as 1 over v. The reason is because as v increases, our policy can track the long-term dynamics better. That's why the first term decreases. The second term actually comes from the uncertain payoff. Remember, n is actually the mean number of tasks per client. So as n increases, then this payoff regret due to uncertain payoff also decreases. The third term actually is due to the backlogged clients or tasks in the system. Remember, the backlogged clients increase linearly in v. But then this effect is amortized by considering a large time horizon t. So we divide it by capital T here. Okay, so note that this payoff regret bound actually holds for any finite time t. And in particular, if you let t goes to infinity, you can slowly increase v, and then the first term and third term will vanish, and then the middle term will become dominate in the stationary regime when t goes to infinity. And also I want to mention that the square root of log n over n regret actually holds for any payoff vector distribution with finite support. Okay, and this is actually matches this optimal instance independent regret 1 over square root of n in the multi-m Bandit literature up to a square root of log n factor. Okay. So let me show you a performance comparison using the numerical experiments based on our running example. It turns out that, so here, this is the Oracle upper bound, and our policy actually outperforms the queue-based control policy and the myopic matching policy. And also you can see that as v gets large, the gap to the Oracle upper bound of our policy is actually become small. Okay. So how much time do we have? Oh, 5 minutes. Okay. Okay. I think so I'm going to give you a very brief proof overview of the main result of payoff regret. I hope that kind of show you some of the key steps in our analysis, like how we combine Q and learning. So the main idea is that we're going to use system with perfect payoff as a reference. So on the left-hand side is the system with perfect payoff. On the right-hand side is system with uncertain payoff. So for the perfect payoff, so we're going to apply this Lyapunov drift plus payoff gap analysis. And in particular, we are able to show the drift plus payoff gap is roughly bounded by 1 over v. And from there, we can conclude the payoff gap is bounded by 1 over v, plus the second term capture the backlogged client in the system. And now for the uncertain payoff, we follow the same roadmap. But the difference is that the drift plus payoff gap is actually now bounded by roughly 1 over v, plus additional term, which I called A1t. So that is the kind of the learning loss due to the uncertain payoff. And now to finish the proof, we essentially need to bound this learning loss, A1t. And that will give you the middle term. So then essentially this will give our final payoff gap. But let me briefly tell you the main steps in details. So the first step is about this Lyapunov drift plus payoff gap analysis. We use the quadratic function of the number of clients of each class, normalized by the arrival rate as a Lyapunov function. We also use this delta t to capture the payoff gap, but adjusted by this gamma to match our design of a policy. And now you can study the drift of the Lyapunov function. You can show that the expected Lyapunov drift plus this payoff gap is actually upper bounded by roughly 1 over v plus this additional learning loss term A1t. And once you have this lemma, you can actually do a very quick telescope sum from t equal to 0 to capital T. And using the property that the Lyapunov function is 0 at the beginning and is non-negative always, to conclude to get an upper bound on the payoff gap. Okay, and now the final thing that you need to do is that this delta t is not exactly the payoff gap because of the adjustment by gamma, but that's easily to deal with. That will give you additional term due to the backlogged client in the system. And then since we already have a bound on the expected value of backlogged clients, we can plug that in and then get the final payoff gap. So now the remaining thing is just to bound this average payoff. So what's this A1t? So this A1t actually can be viewed as a product of two errors. The first error is the learning error. So that's the difference between the UCB estimator and then the true payoff. The second term, we call it controlling error, because that's the difference between assignment of our policy and the assignment of our policy if the true payoff were known. Okay. So this A1t is just the multiplier of these two errors. And to bound this A1t, we're actually going to separate these two effects into two terms. The first term captures the learning error. The second term captures the controlling error. And for the second term, the learning error, the crucial thing is that the UCB estimator is likely to overestimate the true payoff, but the overestimate amount is likely to decrease as you continuously pull the arm, in particular as the probability of assignment accumulates. So to execute this idea, we're going to plug in the overestimate amount, replace that by the UCB bound. It's roughly 1 over square root of the number of times you select this server and times the probability. But now there's a slight technical difficulty, is that this h is the actual number of times you pull this server j. P is actually the probability you put in the j. So these two quantities are not exactly the same. And then there's also a dependency issue. But here we're using a rather simple martingale argument. Essentially, we can show that this quantity is roughly the same if you replace the probability by the increment of the actual number of pools. And once you have this, then it's easy to convince you that this sum is roughly 1 over square root of k, sum from k from 1 to capital N, and that gives you the square root of n upper bound, regret upper bound. So that's how we show bound the A2t. For the A3t, that is due to the controlling error. The good news is that since UCB is likely to overestimate, so this difference is likely to be negative, okay, which is a good thing. But now there's still a very tiny probability this difference could be positive. And this bad event actually happens with some probability, like diminishing when you have pulling the arms many times. But now you time the error times the p hat, which is the ideal like assignment, not the true assignment. So it is possible that this p hat accumulates, but this h remains small. So in this case, both of the terms could be large. So you get this A3t could still be like unbounded. Now the crucial thing is that luckily, due to our design of algorithm, we are able to bound this controlling error. So in particular, we're going to bound this error by at most a multiplicative factor. And the reason is that this logarithmic utility promotes fairness. And because of fairness, no matter how bad the UCB estimates are, there's no client assignments are kind of heavily skewed. So every client are able to learn to some extent. So that's why we have this bound on the controlling error. And once you have this, then you can replace p hat by p roughly, and then following the previous analysis to complete the proof. So that's how we bound this A3T. And this, the whole thing can finish the proof. So now let me quickly conclude my talk. So in this talk, motivated by operation of online service platforms, we try to combine queuing and learning. And then the important thing we learn is that learning cannot ignore queuing dynamics because myopic decisions do not produce good long-term performance. Also, queuing cannot ignore learning in the sense that queuing can cause delay to the learning. And also there are closed loop interactions between these two. So our contribution is to develop this utility-guided online learning and control policy, and we prove this achieves a low finite time regret. So I think our work only touches on tip and iceberg in this area. There are many interesting extensions and open problems. For example, you can imagine in the online service platform, there also exists uncertainty in server side. For example, the service time could be random. Also, in many online platforms, the decisions may not be centralized. Instead, they're decentralized. It turns out that since our policy is based on convex program, so we can develop a dual algorithm, which is also called virtual queue algorithm, to deal with server-side uncertainty and also leads to decentralized decisions. There are also a number of very interesting open problems I want to briefly mention. In this work, we assume the unknown payoff vector has a finite discrete distribution. So what if this payoff vector has a continuous distribution? Our current analysis is not able to deal with this. Also importantly, the regret lower bound we show is a square root of log n over n. It will be interesting to show this lower bound is fundamental. Also, it will be interesting to look at this so-called instance-dependent setting where we assume the payoff vector is generated according to a fixed distribution beforehand. Then according to the multi and Bandit literature, we can get a lower regret, log n over n. But how to achieve this in our setting is unclear. You can also consider a scenario where you have a growing number of servers. Our current regret bound grows with the number of servers. But if you impose some additional structures like linear bandits, maybe you can get a lower regret, even with a growing number of servers. And then you can also try to consider other types of learning instead of UCB, for example, like Thompson sampling, and see what's the effect. And then lastly, I want to mention that in this talk, we focus exclusively on online learning. But for online service platform, there also exists abundant historical data. So how to combine offline learning from historical data with online learning using online feedback is also interesting. So with that, I want to conclude my talk. And then here's a reference in case you would like to know more about this work. And thank you for your attention.
For a client which is assigned no job is going to be minus infinity, you know. So it's never going to be, you formulated the optimization problem and there was a log term for each client, right?
Yes.
So you need that every client should be assigned at least one job? Or?
Yeah, so you need to assign like a tiny probability because otherwise, so even if you have a huge number of clients in the system, you are still able to assign maybe a tiny probability to that.
It's not discretized.
Yeah, so it's still not negative infinity. Yes.
Okay. Yeah.
So what are the results we have? How do they depend on C star?
C star? Actually, no dependence as long as, okay, so the only dependence is through the number of class, I. It does not depend on the particular value of the underlying true payoff. So that's why we say it's kind of close to this so-called instance-independent regret. Yes. Yeah. Yes. Yeah. The lower bound, I haven't been able to talk about lower bound. Yeah, so we don't have a rigorous lower bound. This kind of suggests that this square root of log n over n is maybe something cannot be avoided in this instance independent setting. But the rigorous proving this in our setting is still open. Yeah. Yeah, so the reason is because we assume some structure on the client payoffs. So if there are many clients, you might be able to get some information about this new client from the previous client. So that may help you to learn these new clients' payoffs. So if each client is like indeed an independent multi and bandit problem, then this square root of log n over n is the fundamental lower bound. But there's some dependency among different clients. So we're not able to exclude that. Yes. Yes, so you can maximize over all the payoff vectors subject to the payoff vector distribution is finite, has finite support. Sorry? Is there also a problem dependent from which you can get? Yeah, so that's another open problem as I mentioned. So if you fix the vector distribution beforehand, you can possibly get log n over n. But right now, we're not able to get that. It depends on the cardinality support. That is capital I.
Okay, so your thing is not instant.
Yeah, in terms of the particular values.